Okay, in this video we're going to be looking at how to test a claim or construct a hypothesis testing dealing with two means where the samples are independent. Okay, so we'll look at situations where the standard deviation of two population means are unknown and are not assumed to be equal. Okay, now it is important that you do know the differences between independent and dependent samples as we see here. Now two samples are independent, which is what we're going to be looking at here in this video. If the sample values from one population are not related to or somehow naturally paired or match with sample values from the other population. Okay, so that means that the sample values from one population have no relationship with the sample values from the second population. Now for dependent samples, here two samples are dependent if the sample values are paired. That means that each pair of sample values consists of two measurements from the same subject, or each pair of sample values consists of matched pairs, where the matching is based on the same inherent relationship. In other words, let's say for one class you give a pretest at the beginning of the semester, and then at the end of the semester you give a post-test to that same class, to that same group of people. That would be considered dependent sampling, okay? Because you have like two measurements from the same subject, a pretest and a post-test. Alright, first of all, we need to give you some notation that is related to this particular video on two means with independent samples. So here we'll start with the notation. And again, we're going to be dealing with population 1 and also population 2. Now, for a population mean, usually the population mean is denoted by the Greek letter sigma. But for the first population, we use mu sub 1. Greek letter mu is the population mean, so mu sub 1 would be the mean of the first population, and mu sub 2 would be the mean of the second population. Then, and then we have a sample mean. Of course, the sample mean is always x bar, so for the first population it'll be x1 bar, and then x2 bar will be the sample mean coming from the second population. And then you have your population standard deviation, which is denoted by the Greek letter sigma. So in this case here, sigma sub 1 will be the population standard deviation from the first population, and then sigma sub 2 will be the standard deviation from the second population. Now for the sample size, that's usually n. So n1 will be the sample size coming from the first population. n2 will be the sample size coming from the second population. And then finally you have your sample standard deviation. So in this case here, S1 will be the standard deviation, or the sample standard deviation coming from the first population, and S2 will be the sample standard deviation coming from the second population. Okay, so that's the notation that's being used in this particular section. Okay, now, when we test a claim for two means dealing with independent samples, so writing a confidence interval estimate for two means where the samples are independent, we have four requirements that need to be met. So here, let me give you those requirements. Okay. The first requirement is this. The standard deviation from the first population and the standard deviation of the second population, that's sigma 1 and sigma 2, are unknown and is not assumed that sigma 1 equals sigma 2. That's the first requirement. The second requirement is this. The two samples are independent. And I've already defined what independent means, that the sample from the first population have no relationship with the sample of the second population. Second sample from the other population. Number 3. Both samples have to be simple random samples. Both samples are simple random samples. And then number 4, either the two samples are both large, and we use 30 as a guideline for something being for a large sample. N1 is bigger than 30 and N2 is bigger than 30. That's the sample size from the first population, or the first sample size has to be bigger than 30, and the second sample size has to be bigger than 30 as well. Or both are from normally distributed populations. So those are the 4 requirements for either testing a claim about two means with independent samples or writing a confidence interval estimate about two means with independent samples. Okay. Right. So once those 4 requirements are met, we can do a confidence interval or a hypothesis testing. Alright, now let's start off with the test statistic for two means with independent samples. So this is going to be your test statistic for two means. And here we're going to be dealing with independent samples. And in another video, we're going to be dealing with dependent samples when we test a claim about two means. Okay. So the test statistic is going to be this. Here we're going to be using a t-test statistic because pretty much it is a t-test. That's going to be x1 bar minus x2 bar minus mu sub 1 minus mu sub 2. That's divided by the square root of s1 squared over n1 plus s2 squared over N2. So that's going to be your test statistic, and this is where mu sub 1 minus mu sub 2 is assumed from the null hypothesis to be 0. Okay. Now you'll be given x1 bar and x2 bar, then s1 and s2, and then n1 and n2. So you'll be substituting those values into this formula here, and then calculate what that test statistic is. Okay, now in this case here, we'll be using the graphing calculator, the TI-83 or the 84 plus calculator will help you find out what your t-test statistic is going to be. Okay, now degrees of freedom. Which is denoted by DF. Degrees of freedom is always going to be this. Since we're dealing with two means, we're going to use the smaller of n1 minus 1 and n2 minus 1. Okay, so we're going to be using the smaller of these two values as your degrees of freedom. Usually the degrees of freedom for one sample will be n minus 1, but here we're dealing with two samples. So we're going to be using the smaller of the two, and it's the conservative number that we're going to be using. Now your calculator will give you the degrees of freedom, but it uses a totally different formula to calculate its degrees of freedom. Here we're going to be using the conservative number of degrees of freedom, either n1 minus 1 or n2 minus 1. Now to calculate a p-value, you'll use table A-3, which is the t distribution, or use technology. And here the TI-83 or the 84 plus calculator does calculate the p-value as well. And for those of you who are not familiar with table A-3, which is the t distribution, which is the critical t values, this is it. The left column is your degrees of freedom. You'll use the smaller of n1 minus 1 and n2 minus 1. The top row is the area in one tail. The row underneath it is the area in two tails. You have to look at your alternative hypothesis to determine whether you have a one-tail test or a two-tail test. Usually a one-tail test will be less than or greater than. Two tails will be usually not equal to. Okay. And that table that I just showed you, that's what you use to find your critical values. So for your critical values, you use table A-3. Okay, the other one is the confidence interval estimate for the differences of your two means. Okay, so let me go and give you that one. Confidence interval estimate. It's a confidence interval estimate of mu1 minus mu2, where your samples are independent. And that confidence interval format is this: x1 bar minus x2 bar minus e. Again, e is your margin of error. That's less than mu1 minus mu2 and less than x1 bar minus x2 bar plus e. Okay. So that's going to be the format for your confidence interval estimate. Usually x1 bar and x2 bar will be given to you, but for the margin of error you'll have to calculate that. So e, and we call that the margin of error, that's going to be t of alpha over 2 multiplied by the square root of s1 square over n1 plus s2 square over n2. And again, you'll be given the sample standard deviation for both samples, the sample size for both samples. T of alpha over 2, you have to use table A-3. Okay, so here, this is where your degrees of freedom, as I mentioned earlier, that's the smaller of n1 minus 1 and n2 minus 1. And you'll use table A-3 as I mentioned, which is of course the t distribution. Okay. And of course it's this table right here again. But here with the confidence interval, we'll only use the row that says area in two tails. And of course your degrees of freedom is the smaller of n1 minus 1 and n2 minus 1. Okay, so in this case, let's look at a few examples that are related to doing a hypothesis test and a confidence interval. Okay. I do have my examples here. Alright, in this case here, a study was done using a treatment group and a placebo group. The results are shown in the table. Assume that the two samples are independent simple random samples selected from normally distributed populations, and do not assume that the population standard deviations are equal. Complete parts A and B below. In part A, you're to use a 0.05 significance level and test the claim that the two samples are from population means with the same mean. And in part B, construct a confidence interval suitable for testing the claim that the two samples are from populations with the sample mean. Okay, so let's start off with part A, doing the hypothesis testing, because it did say use a 0.05 significance level. So step number 1 is the original claim written in symbolic form. So in this case here, we're testing the claim that the two samples are from population means, are from populations with the same mean. That means the population mean of the first one has to be the same as the population mean of the second. So mu1 equals mu2. That's how we write that original claim in symbolic form. Step number 2 is writing the opposite of the original claim. Well, if we have mu1 equaling to mu2, then the opposite of this statement will have to be mu1 is not equal to mu2. Okay. So that's the opposite of the original claim. Now step number 3 is writing the null and the alternative hypothesis. So here the null has the equal sign, the alternative does not. In this case here, your original claim has the equal sign in it. So mu1 equaling the mu2 is your null hypothesis. Not only that, that's your claim. And then the opposite is that alternative hypothesis, because the alternative has either greater than, not equal to, or less than. So it'll be mu1 not equal to mu2 as your alternative hypothesis. So that's step number 3. And by the way, do refer to the video for section 8-2, which is the basis of hypothesis testing, if you're not familiar with the 8-step hypothesis testing procedure, because that's what I'm using to test the claim. Now step number four is your level of significance. In this problem, we're told to use a 0.05 significance level. So your alpha level will be 0.05. Okay, now step number 5 is calculating the test statistic. Okay, now let's refer back to that table at the top. Okay, here they're letting mu sub 1 be the treatment and mu sub 2 be the placebo. So that means for the treatment, N1 is your sample size. That's 30. Oops. X bar 1 will be 2.36, or X1 bar will be 2.36. S1 is going to be 0.83. Okay, now for the placebo, they're letting mu sub 2 be the placebo, so that means that N sub 2 will have to be 40. And X bar sub 2, or X2 bar, will have to be 2.62. And S2 is S2 will have to be 0.82. Okay, so now we're going to use all of these given data values here to calculate our test statistic. And it is a t-test, so we will have to use that t formula, so it'll be t is equal to whatever we get from our TI-83 and 84 plus calculator. Okay. So what we're going to do here is press this button, which is a stat key. And then you're going to hit your right arrow key to highlight test. And then we're going to select this menu item that says to samp t test. That's this menu item right here. To samp t test. That's a to sample t test. And then press enter. Okay, now for the input, you're going to have to highlight either data or stats. Here we only have the stats. If we have for the data, we would have to have the raw data values where we have to actually manually calculate what your means are and what your standard deviations are for each individual sample. But fortunately, we have just the statistics. So here we want to highlight stats. So we want to put your blinking cursor over stats and then press enter. And then you want to hit your down arrow key to position the cursor on X bar 1. That's the sample mean of the first sample. Well, here's my first sample statistics right here. X1, that's 2.36. So we'll type in 2.36, then press enter. S sub X is your standard deviation of the first sample. That's going to be 0.83. We'll type that in and then hit enter. N1 is the first sample size. In this case, that's 30. So we type in 30 and then press enter. Now you got X2 bar. In this case here, x2 bar, that's the mean of the second sample, that's 2.62. And then hit enter. S sub x sub 2, that's the sample standard deviation of the second sample, that's 0.82. And then hit enter. N2 is your second sample size, that's going to be 40. And then hit enter. Now for mu sub 1, we got three options: not equal to mu sub 2, less than mu sub 2, or greater than mu sub 2. You have to look at your alternative hypothesis to determine which one you're going to have to use here. And in this case, your alternative has not equal to in it. So that means we need to highlight the one that says not equal to mu sub 2. So we want to put the cursor above, not equal to mu sub 2, and hit enter to highlight it. Okay? And then you're going to hit your down arrow key. For the pooled, you'll have the option of yes or no. You'll always choose no. Okay? Because we're not dealing with pooled samples here. And then you're gonna hit your down arrow key to highlight calculate. Okay? And then you'll press enter. Okay, and your screen should look like this. Now in this case here, under mu1 not equal to mu2, the t is your test statistic here. That's in this case negative 1.3036999062. Now we're going to round that off to 2 decimal places, so that t will be negative 1.30. So the test statistic there is negative 1.30. Okay? Now, it's much easier to do it that way than it is with this formula that I gave you. Pretty much you just substitute x1 and x2. Mu1 minus mu2 is assumed to be 0, so we put 0 there. That comes from the null hypothesis. And then substitute s1, n1, s2, n2. Note that s1 and s2, each one of those will be squared. And then if you were to type all that into the calculator, you'll end up getting negative 1.30 as your test statistic, which is what we have here. Okay, step number 6. We need the p-value. Well, we can get that from the graphing calculator as well. Under the t is lowercase p. That's your p-value. And in this case, we got 0.19714011112. But to 3 decimal places, we're going to say 0.197. So that's going to be your test statistic there, 0.197. Okay. Now, step number 7 is the decision rule. And the decision rule is always this: if your p-value is less than or equal to alpha, reject the null hypothesis. Otherwise, we fail to reject the null hypothesis. Now, in this case, our p-value from step number 6 is 0.197. And your alpha level was 0.05 from step 4. Now, if you compare those two, you can see that 0.197 is greater than 0.05. So this does not satisfy the decision rule. So that means we're going to have to fail to reject the null hypothesis. So here we fail to reject the null hypothesis. And then step number 8 is the conclusion, written in simple non-technical terms. Now, the claim is the null, and we fail to reject the null. Okay, so that means our statement will be this: there is not sufficient evidence to reject the claim at the two samples are from populations with the same mean. Okay. Because we failed to reject the null. The null was the claim, by the way, so there's no sufficient evidence to reject that claim that the two samples are from populations with the same mean. Okay, so part A was the hypothesis test. In part B, you were asked to construct a confidence interval suitable for testing the claim that the two samples are from populations with the same mean. So here's part B, doing the confidence interval. Okay, now in this case here, if you recall, we have to find out what our correct confidence level is going to be. Here we have a two-tailed test. Now if you recall, the alternative hypothesis tells you what type of test you have. We have not equal to, so that tells me we have a two-tailed test. And that means the confidence level is always going to be 1 minus that level of significance. Okay. In the last video, I told you when you have a two-tailed test, the confidence level is 1 minus the alpha level or level of significance. But for a one-tailed test, whether it's left-tailed or right-tailed, then your confidence level will be 1 minus 2 times the alpha level. But here, a two-tailed test means your confidence level is 1 minus that alpha level, which will be 1 minus 0.05, which will be 0.95, or 95%. So here we're going to be dealing with a 95% confidence level. So we're constructing a 95% confidence level. Okay, now let's use our graphing calculator to do this. Because we can do the use the graphing calculator to get the confidence interval, and I'll show you how to do that. Press the stat key, and then you're going to hit your right arrow key to test. Now the one that we want to select will be the 2-samp t interval. That's going to be this menu item right here. 2-samp t interval is the one that you want to select. And then you're going to press enter. Now we're dealing with stats, so we're going to leave that alone. Now for x1, S1, N1, x2, S2, and N2, they're the same. Because we did a confidence interval about the two means with independent samples for this particular problem. So these data values remain the same. So here we're going to use our down arrow key. As you can see, x1 bar is still 2.36, S1 is 0.83, N1 is 30, x2 bar is 2.62, S sub 2 is 0.82, N2 is 40. But our confidence level, we came over 95%, so we need to change that to 95%. Okay. Then down arrow. It's still going to be no for pooled. Down arrow to highlight calculate. And then hit enter. Now, those decimal values in the parentheses represent your confidence interval. Now, DF, they use a different degrees of freedom. They use a different formula than what we would be using if we were to do this manually. They're using the formula for the degrees of freedom that's programmed into this calculator here. Then you got your X1 bar, X2 bar, S1, S2, and then N1 and N2. So here, in this case here, this is your confidence interval. Rounded to 3 decimal places. I should have mentioned that. As in the other one, you want to round your confidence interval limits to 3 decimal places. That's very important. So in this case here, our confidence interval would be this. Negative 0.6, and I'm going to round this up to negative 0.659. Is less than mu1 minus mu2, and less than 0.139. Okay, excuse me. Okay, so that's the confidence interval here. Now, in this case here, we interpret that as saying that we are 95% confident that the differences of the two sample means, the two population means, the differences in the two population means is between negative 0.659 and 0.139. And I'd like to show you how I use the actual formula with the margin of error to do this one. You have to find out that it was 95% confidence level, and my degrees of freedom, I had to use the 30 instead of the 40, because in this case here, I have to use the smaller of these two right here. This one is 30, that's the smallest. The smaller of the two is 30. 30 minus 1 will be 29. And then using table A-3, which is that t-distribution table, that test statistic was 2.045. And then I use this formula here. I just substituted the t of alpha over 2 with 2.045 and S1, S2, N1, and N2. Calculated all this to get 0.4078. Okay, and then I used that confidence interval formula and substituted those values here. Now notice my limits are a little bit different from what I've used when I did the did it with the graphing calculator. Okay, and that's because of the conservative degrees of freedom that we used here. Your calculator, the TI-83 or 84 plus calculator, uses a different formula to calculate its degrees of freedom. Okay, so that's why if you did it manually this way, it'll be a little bit off than using the TI-83 of the 84 plus calculator. Okay, so that's one example. That's parts A and B of doing a confidence interval and a testing, hypothesis testing. Okay, now let's look at another example of just this. Okay, take a look at example E2. Researchers conducted a study to determine whether magnets are effective in treating back pain. The results are shown in the table for the treatment with magnets group and the sham or placebo group. The results are a measure of reduction in back pain. Assume that the two samples are independent, simple random samples selected from normally distributed populations, and do not assume that the population standard deviations are equal. Complete parts A and B below. So here we're going to be in part A using a 0.05 significance level and test the claim that those treatments with magnets have a greater mean reduction in pain than those given a sham treatment. And part B, construct a confidence interval suitable for testing the claim that those that those treated with magnets have greater mean reduction in pain than those given a sham treatment. Okay, so now here's part A. Constructing just doing the hypothesis testing. Okay, so here's step number 1. We need the original claim in its symbolic form. Now, in this case here, we're testing the claim that those treated with magnets have a greater mean pain reduction than those given the sham treatment. So here, the treatment is mu sub 1, the sham treatment, or the placebo, is mu sub 2. So here, mu 1 must be greater than mu 2. Okay. Those treated with the magnets must have a greater mean pain reduction than those given a sham treatment. Mu 1 has to be greater than mu 2. That's your original claim. Step number 2 is the opposite of the original claim. So the opposite of greater than will have to be less than or equal to. So the mu 1 is less than or equal to mu sub 2. And then step number 3 is writing your null and your alternative hypothesis. The alternative is the one that does not have the equal sign in it, and it's this one right here. Mu 1 is greater than mu 2. That's going to be that's the original claim. And the alternative always has the equal sign in it, so it'll be mu 1 equals mu 2. Alright, step number 4 is the level of significance. That's going to be 0.05. That's given to us in the problem because we're using a 0.05 level of significance to test the claim. Step number 5 is simply calculating the test statistic. Now here we can use the graphing calculator for this one. Now, for the treatment, that's your mu sub 1, and it has sample statistics there. So here for the treatment, if mu sub 1 is the treatment, then N1 will be that sample size, which is 29. So here N1 is 29. X bar 1 is 0.49. S1 is going to be 0.81. Okay, now the sham treatment is represented by mu sub 2. So N2, the sample size of the second, is 29. And X bar 2 has to be 0.45. And S2 is S, that's the second one. S2, that's 1.49. Now here we can type all of those sample statistics in our graphing calculator using that same procedure that we did in the last example. Okay, so here it is. Go ahead and press the stat key, and then you're going to hit your right arrow key for test, and the one you're going to select is 2SAMP t-test. 2SAMP t-test. Then hit enter. We're dealing with sample statistics, so stats should already be highlighted, not the data, just your stats. Now hit your down arrow key to find or to type in X bar 1, which is 0.49, and then press enter. S1, that's 0.81, and enter. N1, that's 29. Type in 29 and then press enter. Now let's do the second sample statistics. X bar 2 is 0.45. So type that in and press enter. S2, that's your 1.49. Type that in and press enter. N2, 29. Then press enter. Now for the mu1, we have to choose not equal to mu2, less than mu2, or greater than mu2. Let's look at our alternative hypothesis here. That will tell us which one we need to select. The alternative hypothesis says mu1 is greater than mu2. So we need to select the one that says greater than mu2, which is this one right here. So we need to put the blinking cursor on top of greater than mu sub 2 and press enter to highlight it. Then hit your down arrow key. For pooled, we select no, and it will always be no. Then hit your down arrow key to highlight calculate. The blinking cursor should be on calculate, and then press enter. Okay, so now we have our test statistic here, which is step number 5. Your t in this case is 0.127013373, so to 2 decimal places it will be 0.13. So here t is equal to 0.13. Alright, step number 6. We need to calculate or find out what the p-value is. That's also on the calculator as well. So let me pull this calculator back up. You'll see that t is this. Underneath it is your p. That's your p-value. In this case, 0.4497594522. But to 3 decimal places, we're going to say 0.450. So 0.450 is your p-value. Alright, step number 7. Is the decision rule, and that's this. If the p-value is less than or equal to alpha, you're going to reject the null hypothesis. And here in this case, our p-value is 0.450. Your alpha level is 0.05. And we're going to compare those two. 0.450 is greater than 0.05. So this does not satisfy the decision rule, so that means we must fail to reject the null hypothesis. Fail to reject the null hypothesis. Okay. Now, step number 8 is writing the conclusion using simple non-technical terms. The claim was the alternative hypothesis, but we failed to reject the null. So there's no way that we can support the claim based on this. So our decision is this, that there is not sufficient evidence to support the claim that those treated with magnets have a greater mean reduction in pain than those given a sham treatment. Okay, so that's the conclusion statement based on that hypothesis test that we just conducted. Okay. Now, part B, we're going to construct a confidence interval suitable for testing a claim that those treated with magnets have a greater mean reduction in pain than those given a sham treatment. Okay, so we want a confidence interval. So this is part B. Okay, now we have to find out what type of test that we had, well, whether it was a left tail or right tail or a two-tail test. Here we have a right tail test. Okay, so in this case here, left tail or right tail is a one-tail test, so that means the confidence level is 1 minus 2 times the alpha level. Okay, the last example we had a two-tail test, so it was 1 minus the alpha level. But now it's a one-tail test, so we got to do 1 minus 2 times its alpha level. So in this case here, 1 minus 2 times, my alpha level or level of significance was 0.05. So 1 minus 2 times 0.05 would give me 0.90, which as a percent will be 90%. So we're going to be constructing a 90% confidence interval estimate in this case. Okay, using the calculator, let's see here. Go to Stat, right arrow to Test. Okay, now the one we want to select, of course, is your 2-samp T interval. That's this menu item right here, 2-samp T interval. Press enter. Stat should already be highlighted, and our data value should already be available because we already did the hypothesis testing back in part A using that same sample data. Okay, so let's use our down arrow key to see what we need to change. We need to change that confidence level from 95% to 90%. So we type in 90, then press enter. Pooled is always going to be no, so we hit the down arrow key, highlight calculate, and then press enter. Okay, and at the top, those decimal values in the parentheses is the confidence interval. Those are your endpoints for your confidence interval. So in this case here, rounded to 3 decimal places, it would be negative 0.489 is less than mu1 minus mu2 and less than your upper confidence limit is 0.569. Okay. So in this case here, we can say that we are 90% confident that the mean differences in pain reduction using in both treatments, the mean differences in pain reduction will be negative 0.489 and 5.569 will be in between those two limits. And notice that your lower limit is negative and the upper limit is positive. So that means that there is no sufficient evidence in this case, because the confidence interval limit does contain, the confidence interval does contain 0 in it. Okay. Now, doing it by hand, it will be like this. And it will be a little bit, the limits will be a little bit different from the ones if you were to do it later. Okay. And you can see here that the test statistic was 1.6, t-value, or the critical t-value, is 1.701, because I'm dealing with a 90% confidence interval and 28 degrees of freedom. Okay. Okay, I'm going to do one more example of just this. And that's going to be this one right here. And that will conclude this particular video. A study was done on skull sizes of humans during different time periods. The results are shown in the table. Assume that the two samples are independent, simple random samples selected from normally distributed populations, and do not assume that the population standard deviations are equal. Complete parts A and B below. In part A, you're to use a 0.01 significance level and test the claim that the mean skull breadth in 400 BC is less than the mean skull breadth in AD 150. And then part B, construct a confidence interval suitable for testing the claim that the mean skull breadth in 400 BC is less than the mean skull breadth in AD 150. Okay. So let's start off with part A. And here's the table that we'll be using here. Now, step number 1 is to state the original claim in symbolic form. Now, it says here that the mean skull breadth in 400 BC is less than the mean skull breadth in AD 500. Since mu sub 1 is the 400 BC, mu sub 2 is AD 150, we can say mu sub 1 is less than mu sub 2. And then step number 2 is the opposite of the original claim. The opposite of less than will be greater than or equal to, so that means mu sub 1 is greater than or equal to mu sub 2. And then step 3 is writing the null and the alternative hypothesis. Okay, well, the null always has the equal sign. The alternative does not. It either has less than or greater than or not equal to. So we have to use the one that has the less than symbol exclusively, which is mu 1 is less than mu sub 2. That's your alternative hypothesis, and that's your original claim. So your null is mu 1 equals mu sub 2. And then step number 4 is the level of significance. We're using a 0.01 level of significance this time. So your alpha is equal to 0.01. And then step number 5 is we're going to use that graphing calculator to calculate our test statistic. 400 BC represents the mu sub 1. So N1 was 35. N1 is 35. X bar 1 is 132.91. And S was 5.48. I'm getting those data values from this table up here. And then for AD 150, which is mu sub 2, N1 is 35. Now N1, N2 is 35. X2 bar is 134.77. And S2 was 5.36. And this should be S1 here for 5.48. Okay. So now let's use our graphing calculator to calculate your t-test statistic. Okay. We press the stat key, use our right arrow key to highlight test. The one we want to select is your 2-samp t-test. 2-samp t-test. That's this menu item here. Highlight that and press enter. Stat should already be highlighted, so go ahead and press, well, hit your down arrow key. X1 is, well, X bar 1 is 132.91, so we're going to type in 132.91, then hit enter. S1, that's your sample standard deviation, 5.48. N1, that's going to be 35. And then X bar 2, that's the sample mean of the second sample. That's 134.77. Hit enter. X2, that's this 5.36. Hit enter. N2, that's your 35. Hit enter. Now for the mu1, it's either going to be one of those three based on your alternative hypothesis. And in this case, the alternative hypothesis says mu1 is less than mu2. So we need to highlight less than. So we put the blinking cursor above the less than mu sub 2 and then press enter to highlight it. And then we press that down arrow key. For pooled, we always select no. Down arrow key to highlight calculate, and then press enter. Now under mu1 less than mu2, here's your test statistic right here. Negative 1.43550956, but we round this off to 2 decimal places. It will be negative 1.44. So that's your test statistic, negative 1.44, which is step number 5. Step number 6 is your p-value, and that comes from the graphing calculator as well. Under your t, test statistic is p, which is your p-value. To 3 decimal places, this will be 0.078. So your p-value there is 0.078. Okay, now step number 7 is the decision rule. And that's this: if your p-value is less than or equal to alpha, reject the null hypothesis. Alright, now the p-value there is 0.078. Your alpha level is 0.01. Now if we compare 0.078, it is greater than 0.01. So this would not satisfy the decision rule, so that means we will fail to reject the null hypothesis. Fail to reject the null hypothesis. And then step number 8 is writing the conclusion in simple non-technical terms. And in this case here, the claim was the alternative hypothesis, but we failed to reject the null hypothesis. So that means we're not able to support the claim. So that means that there is not sufficient evidence to support the claim that the mean skull breadth was less in 4000 BC than in AD 150. Okay. So that alone right there is your hypothesis test. And that's part A. Now in part B, you're asked to construct a confidence interval suitable for testing the claim that the mean skull breadth in 4000 BC is less than the mean skull breadth in AD 150. Okay, so part B is the confidence interval. Alright, but we do need to find out what the correct confidence level is going to be. Okay, the alternative hypothesis says less than. So that tells me I have a left tail test. Okay, simply put, it's a one tail test. So that means that my confidence level, abbreviated CL, will be 1 minus 2 times the level of significance. And my level of significance was 0.01, so that means I'll have 1 minus 2 times 0.01, which will be 0.98 or 98%. So that means I'm going to have a 98% confidence interval that I need to construct. Okay, so let's use our graphing calculator to do that. Okay, so here, press the stat key, go to test using your right arrow key, use the down arrow key to select the menu item that says 2samp t interval. 2samp t interval. Hit enter. Stats should be highlighted, so go ahead and press enter. And notice our data values that we got for the 4000 BC and AD 150 are already there. We just need to change our confidence level to 98%. So we just type in 98%. Use your down arrow key. No should be always be selected for pooled. Highlight calculate, or put the blinking cursor on calculate, and then press enter. And there's our confidence interval limits at the very top. And it's already to 3 decimal places. So this lower limit is negative 4.947. And that's less than mu1 minus mu2 and less than 1.227. Okay. So we can say that we are 98% confident that the differences in the mean skull breadth in 400 BC and AD 150 is between negative 4.947 and 1.227. Okay. And I'll also show you how this is done manually. At least you just get a brief looking at it. Here, my critical T value was 2.441 using 34 degrees of freedom. N1 and N2 was 35, so obviously the smaller, 35 is just have to be used anyway. So 35 minus 1 is 34. 34 degrees of freedom and 0.01 in one tail, or 98% confidence level, will be 2.441. And then the margin of error was 3.16282. And notice that my confidence interval limits are a little bit different, or a little bit off, using it this way than it is using the calculator, because of the fact that the calculator uses a formula that calculates the degrees of freedom. We're using a more conservative degrees of freedom, so that's why your limits may be off if you were to do it manually. And because the confidence interval contains 0, it does support the conclusion that there's not sufficient evidence to support the claim. Okay? Alright, so this will conclude this particular video on two means when we're dealing with independent samples.